Okay. All right. So so all right. So you can see the picture. Yes. So I have C here, which is a singular K cube. Okay, so this bottom here is 0, 1 to the K. This top is the interval 0, 1. This little here is S, this distance here is S. And what I'm doing is I'm flowing basically by the flow of X. I'm flowing, so I'm flowing by the, so this will be, so this bottom is, this is image C. And this top will be image of phi S of C. Okay. And so when S is very small, see what happens to a point here? It moves along a flow line of X, right? These will be flow lines of X, yes? Integral curves of X, right? These are integral curves of X. So when S is very small, these integral curves will be tangent to X, right? So here I'll have X pointing. This will be X at the bottom here, right? Yes? Yes, you
Yes,
see
sir.
the, yes, okay. So now I want to calculate what is my, this pullback PS star of omega. So let omega be a K plus 1 form in M. And let P be a point in M, and V1 to Vk tangent vectors at P. Okay. So then what is PS star of omega at the point P acting on V1 to Vk? So this will be the integral from 0 to 1, right? I'll have omega of, so phi t of P. So instead of, my homotopy is phi of St, right? S is fixed. So this will be phi of St of P. And then I'll have del T of phi St of P. Yes. And then I'll have d phi St at P V1 up to d phi, sorry, d phi St at P of Ek, sorry, Vk, whole thing dt, right? Yes, right? This is my dual of the prism operator acting on forms. Yes, right? Yes, are you there?
Yes, sir.
Hello.
Yes, yes, yes.
Yeah, this is fine. Yes, okay. Now, what is this del del t of phi st of p? So if gamma of t is equal to phi t of p, this is an integral curve of x. So let me not put the if. So gamma t, so equal to phi t of p, this is an integral curve of x. So gamma prime t is equal to x of gamma t. And what is ddt of, so what I have here is gamma of st, right? So what is ddt of gamma of st? So by the chain rule, this will be s times gamma prime of st, right? Yes. So
Yes, sir.
this equal to s of x of gamma of st. Yes. Okay.
Right, right.
So what will this del del t of phi stp be? This will be s times x at the point phi st of p, right? And then I'll have d phi st at p v1 up to d phi st at p vk. Okay, and then I have this integral dt. Okay, now what happens as s tends to 0? Well, this omega is linear, so this s will come out of here, right? I'll get an s coming out. So as s tends to 0, this should tend to 0 like s times some constant, right? So what I should do is divide by s. So I look at 1 over s times ps star omega. So I put a 1 over s here. I put a 1 over s and I put a 1 over s here. All right. Then this 1 over s will cancel with this s here. Yes.
Yes, yes.
So this becomes now integral 0 to 1 omega phi stp x at phi stp d phi st at p e1 sorry v1 up to d phi st at p of vk dt. Now what happens is s tends to 0. As s tends to 0, phi st p tends to phi 0 of p, right? Which is just identity. So this becomes omega p. So this converges to integral 0 to 1 omega p. And what happens to x of phi stp? So phi stp is converging to p. So x of this converges to xp, right? So this converges to xp, right? And then what happens to d phi st at p? Well, phi st is converging to identity as s tends to 0 for t fixed. So it converges also in the C1 topology. In fact, all of its derivatives of the phi t's converge to the derivatives of identity as t tends to 0. So this d phi st will converge to the derivative of the identity, which is the identity. So this will converge to just V1 up to Vk as s tends to 0, dt, okay, as s tends to 0. And so this is nothing but, this now is a constant, it doesn't depend on t. So this is just omega p of xp of V1 to Vk. All right. Is this clear?
Yes.
Okay, now this is a k form which we got from a k plus 1 form. How? By inserting x in the first position. X was a vector field, right? We just inserted x in the first position. Then this becomes a function of k vectors. So it becomes a k form. So this has a name. This is called the interior contraction with x. So this brings us to definition. So interior contraction so if x is a smooth vector field and omega is a k plus 1 form, so define a k form ix omega. This is the interior contraction of omega with x. So this will be a k form by, so ix omega at p acting on V1 to Vk. This is defined to be omega at p acting on x at p and then V1 to Vk. Okay, so p belongs to M, V1 to Vk belong to TPM. Okay. All right. So what we have shown is, so we have shown that 1 over S, the dual of the prism operator corresponding to the flow of X, Ps star omega, this converges to Ix omega as S tends to 0. Okay.
Yes.
All right. So now we're almost coming towards the main result of today, which will be Cartan's magic formula. So it's an infinitesimal homotopy formula. So now we come back to the general prism operator. And we come back to a calculation of the boundary of the general prism operator. So we have P going from CKM to CK plus 1 N. Okay. So PC of T x1 to xk is phi t of C of x1 to xk. What I want to calculate is the boundary of PC, all right? We want to calculate the boundary of PC. So that should be clear from the picture actually. So let's look at the picture and you'll see what the boundary should be. So where's the picture? Here's the picture. So see, this is my PC, right? So what is the boundary of PC? Well, you have the top and the bottom, right? So the top is G composed with C. The bottom is F composed with C. So if the signs work out correctly, we should get a term G composed C minus F composed C, right? That will be top minus bottom, right? That should be one part of the boundary. And what is the rest? Well, the rest is what we're doing is these vertical sides. What are these vertical sides? This vertical boundary, this is the boundary of C, right? And what we're doing is we're taking the boundary of C and then applying the prism operator to the boundary of C. That will give us the vertical sides, right? So the vertical sides should be P of del C, right? So basically we should get the boundary of the prism is the top minus the bottom, that's G composed C minus F composed C. And then up to signs, what will happen? We'll get plus or minus the prism operator applied to the boundary of C, right? Is it clear?
Yeah.
Okay, so let's do this calculation. It's a simple calculation. Let's do it quickly. Okay, so we have to calculate now. So for I equal to, so we have the I alpha faces, right? So we have 1 less than or equal to I less than or equal to k plus 1, and alpha belongs to 0, 1. So first, let's do when I is equal to 1 and alpha belongs to 0, 1. So PC I alpha. So this will be a function of k variables. So let me write them as x1 to xk. This means I put a alpha in the first position, so I should be 1. So this is 1 alpha. PC of 1 alpha. Right. So I put a, so this is so this will be PC of alpha x1 to xk. So that means this will be phi alpha of C of x1 to xk. Right. So when alpha is 0, I'll get phi 0, which is F composed with C. And when alpha is 1, I'll get G, phi 1, which is G. So I'll get G composed with C. So my first two terms are the sum. So alpha goes from 0 to 1 in my boundary of PC of -1 to the I is 1. So I'll get -1 to the 1 plus alpha. PC of 1 alpha will be -1 to the 1 plus 0 F composed with C plus -1 to the 1 plus 1 G composed with C, right? So this gives me G composed with C minus F composed with C. Okay, so that's the top minus the bottom. All right. That's when I is 1. Okay. Now, what about when I belongs to 2 to k plus 1? and alpha belongs to 0, 1. Then my PC I alpha, this will be a function of k variables. Let me write those k variables as t comma x1 to xk. Sorry, xk minus 1. Okay, let me write them as t comma x1 to xk minus 1. Okay. So what will happen? Basically, this will be PC of alpha will be in the ith position. So I is between 2 to k plus 1. So that means basically I will have I minus 1 terms. So I'll get t and then x1 of 2x I minus 2, right? I'll get PC of t comma x1 x I minus 2. So that gives me I minus 1 terms, and then in the ith spot I put an alpha, and then after that I have xi minus 1 up to xk minus 1, right? Is this clear? So this will be phi t of c of x1 to xi minus 2 alpha xi minus 1 xk minus 1. Yes?
Yes, sir.
Okay. So what is this? This is phi t. So this is nothing but phi t of what is inside is c I minus 1 alpha of x1 to xk minus 1, right? What is inside is the I minus 1th alpha face of C, right? Because this alpha is in the I minus 1th spot for C. Yes?
Yes.
Okay, so what is this? This is nothing but, this is P, the prism operator applied to C I minus 1 alpha. So this is PC I minus 1 alpha of t comma x1 to xk minus 1, right? Okay. So this PC I alpha face is P applied to the C I minus 1 alpha face of C. Is this clear? Yeah. So therefore,
Yes.
the sum I goes from 2 to k plus 1. These are the other terms in the boundary. These will be the vertical sides of the boundary of PC. Alpha goes from 0 to 1. Minus 1 to the I plus alpha. PC I alpha. This is the sum I goes from 2 to k plus 1. Alpha goes from 0 to 1. Minus 1 to the I plus alpha. P of C I minus 1 alpha. Right? So this P is a linear operator. I can take this out and I can make I, as I goes from 2 to k plus 1, I minus 1 will go from 1 to k, right? So I can make a change of variable. I put j equal to I minus 1. So then this becomes a sum and I can take the P outside. P is linear. So I take the P outside. This becomes P of sum j goes from 1 to k alpha goes from 0 to 1. So minus 1 to the I becomes j plus 1. So j plus 1 plus alpha. And then I get C of j alpha. So what is inside is nothing but the boundary of C, and there's an extra minus 1 here. So this is nothing but, I get a minus sign coming out. I get minus P of boundary C. Is this clear? Yes?
Yes, 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 sir.
Okay. So therefore we get, finally adding up, we get that boundary of PC is equal to GC minus FC minus P of boundary C. So this is the boundary of the prism. All right. Okay.
Okay.
Now we're almost done. So now we have the following theorem, which will be Cartan's formula. So this is called Cartan's or Cartan's magic formula, some people like to call it. I just call it Cartan's formula. Really, it's an infinitesimal homotopy formula. So here's the formula. It says if X is a smooth vector field on M and omega is a K form on M, then the Lie derivative Lx omega is equal to d of Ix omega plus Ix of d omega. Okay. So we've defined the interior contraction. We know what the Lie derivative is. We've defined the exterior derivative. So is this clear? The right hand side, the left hand side is a K form. The right hand side, these two are also K forms because Ix will decrease the degree by 1 and then d will increase the degree by 1, right? So this will also be a K form and this will also be a K form. Is this clear?
Yes, sir. Yes.
Yes, sir.
Okay, so let phi t.
What is Lx omega?
Sorry?
Lx omega? What is Lx omega? I mean, what?
It's the Lie derivative
is
of
the
omega. We
definition
defined that.
every day?
The Lie derivative. It's the ddt at t equal to 0 of phi t star omega, right? We looked at this already. Didn't we define this? I think, oh no, we didn't define this. I'm sorry. Oh, okay, I'm sorry. Yeah, we didn't talk about it. We talked about Lie derivatives of vector fields, right? So let me just define that. Okay, so, all right, fine. Sorry. Yeah, so brackets here. So Lx omega is equal to ddt at t equal to 0 of phi t star omega. All right, where phi t is the flow of x. So this limit is nothing but this derivative is just the limit t tends to 0. Phi t star omega minus omega divided by t, okay, where phi t is equal to the flow of x. Okay, is this clear? So this is also a K form. Sorry, I forgot to define this Lie derivative of a form. So this is the Lie derivative of a form. All right.
Okay.
Is the definition clear? It's
Yes,
similar to the Lie derivative of a vector field. You in the Lie derivative of a vector field, you use the flow to pull back the vector field to the point P. Here you're using the flow to pull back the form to the point P, right?
Yes, yes.
Okay. Okay, so let's prove this. So we have phi t is the flow of x. So for S small, positive and very much smaller than 1, let so consider the homotopy. Phi st, t belongs to 0, 1, and let ps be the corresponding prism operator. Okay, so then for C in CKM, a singular K cube, what do we have? So if I look at the boundary of PS of C, that is again a K cube, because PS of C will be a K plus 1 cube in M, and then taking its boundary will give me back a K cube. So I can integrate omega over that, right? So I have the integral of omega over boundary of PS of C, and I know what the boundary of PS of C. This will be GC minus FC. So what is G? G is phi t, phi s, and F is identity. So this will be integral over phi s C minus C omega minus integral over PS of boundary C of omega, right? Yes?
Yes, sir. Yes.
Okay, now let me divide everything by S. So I take 1 by S here, I take a 1 by S here, and I take a 1 by S here. And I'm going to let S tend to 0. Okay. So the left-hand side, what happens? By Stokes' theorem and the dual of the prism operator, this becomes 1 by S integral over C of PS star of d omega. Yes. And let me take the 1 by S inside.
Yes,
So,
yes.
okay. So this becomes integral over C 1 by S PS star of d omega, right?
Right, right.
And now here, this integral omega over phi s composed with C will be what? I have to pull back by phi s composed with C. So that's the same as pulling back by C star, and but first by phi s star and then by C star. So that's the same as integral over C of phi s star omega. So this I can write as integral over C of phi s star omega minus omega over S, right? Yes.
Yes, sir. Yes. This is
And now this last term here, I can write this as integral over C of, so I apply this PS will become a PS star omega here, and then this del C will become a D here. So this will become D of 1 by S PS star omega. Okay. Yes.
yes, sir.
Now let S tending to letting S tend to 0, we get So this 1 by s ps star of anything converges to ix of that, right? So this will become integral over c ix of d omega, right? And this phi s star omega minus omega over s, this converges to the Lie derivative by definition. So this will become integral over c lx omega, right? And then this here, inside this 1 by s ps star omega, this converges to ix omega, and that convergence is in the C1 topology actually. So therefore this d of this will converge to d of ix omega. So this will become minus integral over c d of ix omega, right? And this is true for all singular k cube c, right? But then I know if two forms have the same integrals over all k cubes, then they are equal, right? So therefore, I get that ix d omega is equal to lx omega minus d of ix omega. Okay. And so this is Cartan's formula. I just take this term to the other side and I'm done, right? So if you like, this is your infinitesimal homotopy formula. Is the proof clear? Yes. See, what
Yes,
is
sir.
what this corresponds to the boundary of the prism. This corresponds to boundary of an infinitesimal prism. This corresponds to boundary of prism. This Lie derivative corresponds to top and bottom of prism. And this term here corresponds to the vertical sides of the prism. Is it clear?
Yes.
Okay, the only thing is now our prism is infinitesimally thin. You understand? The height is infinitesimally small. Do you get it?
Yes. Yes.
Yeah, the height is, it's an infinitesimal height.
Sir,
That's
I
all.
have a question.
Yes.
Sir, why we can put the limit inside the integral? I mean,
That's because these converge nicely. I mean, the convergence is nice. So I didn't prove that. Okay,
Okay.
let me just stop this meeting and start a new one. I'll just talk for 5 minutes. Any questions you have? Okay, let's just start a fresh meeting. All right. And we can talk about this for 5-10 minutes. Okay.